Hi, thank you for stopping by our paper. I'm Haici from Indiana University, and this is an internship work at Amazon Lab 126. Let's start with a question. What is upmixing? In the music context, upmixing is a process of taking a stereo signal and repurpose it for playing back in the surrounding audio system. In this paper, we ignore the subwoofer, meaning only the 5-channel systems are our output target. It is not something far from our life. The commercial music materials are mostly in the stereo format, and to play them back in a surrounding setup like a home theater or car audio system, you will need some upmixing algorithms. The predominant upmixing methods are based on sound decomposition that separate the original stereo signal into direct and ambient component. And then the ambient component are played back by the rear speakers in the 5-channel settings, adding more spatial effect to the sound scene. However, we believe that the sound effect provided by this approach is limited, especially in the music context. Therefore, in this paper, we propose a upmixing strategy that are more suitable for music upmixing. We postulate a virtual 3D sound space where the original music instruments appear in different spatial locations perceptually. For example, in this figure, each speaker is assigned only one or a few audio sources so that the audience would feel like being surrounded by a live band. Now, an important question to ask is, what is the correct way to place those instruments? Unfortunately, there's not a golden answer to this question. You can probably switch the location of the instrument and you can say the current setup is wrong. Therefore, we decided to factor out the potential spatial images, let a spatial related input to define the correct spatial map of the resulting upmix. There could be different ways of providing spatial images. For example, ask for users' input or reuse the spatial information from an existing 5-channel content. Either way, we will want to disentangle the spatial images and the music content so that we can play with the instrumental positioning independently from the music. We did it by computing the upmixing process backwards, which is disentangling the music content and spatial information from a 5-channel signals representation in order to learn the correct range and format of the spatial images. This is how we train the model. We prepare a variational autoencoder that takes 5-channel signals as input and output. Instead of letting the bottleneck of VAE capture the entire 5-channel signal, we want the latent space to capture spatial information exclusively. We did two things to make it happen. First, we provide an extra stereo input to the decoder. If music content and the spatial images are the two basic ingredients for decoder to reconstruct a 5-channel signal, with all the music content completely provided by this 2-channel input, the only essential information that the bottleneck layer should encode right now is the spatial information. In the meantime, we assume that the spatial maps are mostly constant, meaning the band members are not moving drastically in a short periods of time, so that the musical information should be exponentially larger than the spatial information. Therefore, we can make the features in the latent space small enough to guarantee that only the spatial maps can be captured here. And in our experiment, we make the dimension of the latent variables 50, which is far less than the dimension of the music data. We chose to use a dense net-like architecture for both encoder and decoder to help the information flow during backpropagation. With the VAE model trained in this way talked about, we can provide two different upmixing approaches. The first one, we call it upmixing via style transfer. We want to extract the spatial style from one existing 5-channel music and transfer it to the one we are working on. For example, we want to upmixing an audio format of the song Let It Be by the Beatles to a surrounding version. To do that, we firstly need a 5-channel reference. For example, we have Hey Jude recording in the surrounding format. Now we can use the model to firstly learn the spatial information from the reference music Hey Jude. Then the spatial information are fed into the decoder together with the stereo Let It Be. The output Let It Be music from the decoder is expected to have the same spatial effect as the Hey Jude recording. The advantage of this method is the user doesn't have to be a very knowledgeable music engineer to produce a decent music mixing. They can input their style request by simply providing a reference. But a condition of this approach is the music X and music Y should share similar instrumentation. Another upmixing method is blend upmixing. It uses random spatial images sampled from the learned latent variables so that the users are blended to the spatial control. But the good thing is it doesn't require a reference input to carry the spatial information as Hey Jude does in the previous case. Now I'm going to talk about a big headache for training this model, the lack of the dataset. We need a set of 5-channel music signals of which the instrument specific images are known and can be controlled, which is not available to our knowledge. Therefore, we decided to build our own 5-channel music data using the Muse18 dataset, MuseDB18 dataset, which provides separated instrument stems for over 100 pop songs. We use the vector-based amplitude panning, as known as VAE-based, to position the sources in the virtual 3D sound space. The 5-speaker rendering space we set up follows the ITU standard. And for each instrument, we first specify a virtual sound source direction and then pan it using 2 adjacent speakers to the desired common direction. We visualize the latent vectors formed in the model to understand what is really learned here. In the first 2 plots, each line here represents a 50-dimensional latent vectors. In the figure A, the 2 latent vectors are from 2 samples that share the same music content were with different spatial map. And the difference between those 2 plots indicates that the learned latent variables are not relevant to the music content. In contrast, the 2 plots in the figure B are somewhat tied to each other, you can observe here. And those 2 vectors are from 2 different songs, but are sharing the exact same spatial images of the instrument. And again, the similarity here signifies that the latent vectors are explaining the spatial information rather than the music content. To view it in a more general picture, in figure C and D, we show a dimension reduced latent space. The 5-dimensional vectors in the top figures are now represented by the by each dot in these 3D coordinates. In figure C, we color the dimensional reduced latent vectors by its music content, where you can hardly find any pattern. But in figure D, the same scattering images is now colored by the spatial information. And you can surely notice that the space is now very well structured based on the spatial information. This is another powerful evidence implying that the latent space has correctly captured the spatial information as we expected. Besides, for the scatter plots, we computed the average standard deviation for each group just for a more quantitative description. Aligned with our observation, the standard deviation of the music content groups are remarkably higher than that of the spatial-based groups. After knowing what is really learned in the latent space, we want to evaluate the upmixing performance in a more quantitative way. Our evaluation is mainly on the methods of upmixing via style transfer because spatial maps this method uses can be controlled so that it has a ground truth answer to compare with. Since our model conducts upmixing in a novel way, existing models in the literature are not comparable to us. So we built a simple baseline model by spreading each of the channel in the stereo to the front and rear channels of the same set of these 5-channel speakers. This is an upmixing mode commonly used by home receivers called all-channel stereo. We believe this is a fair baseline to our model because firstly, it set up a lower bound of upmixing performance, which is straightforward for a network to do and does have some decent effect. And secondly, it can perfectly preserve the sound quality of the stereo input because it doesn't involve any source separation, which can produce the artifact. So this can potentially be an advantage over our model. We use 3 objective criterions for evaluation. SD-SDR measures how well the signal is constructed. It is important to use scale-dependent SDR rather than the regular SDR because the scale of the sources are crucial for rendering a correct perceptive virtual direction. Difference of the virtual angle measures how much does the virtual angle of the output diverted from the ground truth one, and we want this number to be as small as possible. Wild measures the Waterston distance between the distribution of the ground truth interchannel level difference and that of the predicted ones. This table shows that our upmixing method outperforms the baseline in every criterion. It is also noteworthy that even with some potential artifacts coming from the implicitly source separation, our model still gets 2 times higher SD-SDR in comparison with the baseline. We also did an A/B-X test and asked the participants to pick between our methods and the baseline, which one is more similar to the ground truth. And the judgment should be made based on the incoming direction of the 4 different sources, respectively, as well as the overall spatial images. The box plot you are looking at shows the percentage of the votes which prefer our model than the baseline. The vocal output here from our model is apparently best rated, maybe because vocals are usually dominant in a pop song. It also has some good influence on the overall spatial effect. To conclude, the spatial information and music content can be disentangled in the latent space of a modified VAE model. And by specifying the spatial images, we define a new approach for upmixing that can be done through style transfer or randomly sampling from the VAE's latent variable. We posted the 5-channel audio samples on our website. Please check them out and listen to them with your 5-channel music device. And feel free to let us know your thoughts. Thank you.